Hello everyone, and welcome back to the Calculus video lecture series. And for today, we are going to be discussing a different type of integral called the definite integral, which has some similarities to the indefinite integral, which you have learned about, and some big differences between the indefinite integral, which you learned about in section 5. Which you learned about in the previous sections. So the definite integral will have some similarities, but it is technically different. Now, from the last video, remember Riemann sums give you an approximation for the area between a curve and the x-axis. It is by nature an approximation, it is not exact. So the biggest way that you can increase the accuracy of the approximation is by increasing the number of subintervals. Increase the number of rectangles because the thinner the rectangles are, and the more rectangles there are, the better the approximation for the area underneath the curve. So in theory, if you had an infinite number of rectangles, then the Riemann sum would be exactly equal to the area between the curve and the x-axis. Also, as the number of rectangles gets larger and larger, as you try to cram more and more rectangles into a finite space, the width of each rectangle is going to approach 0, because as you cram more and more rectangles into a finite space, the thinner and thinner each of them is going to get. So if we were to add together an infinite number of rectangles, we call this the definite integral. And the definite integral gives you the exact area between a function's curve and the x-axis. So that is what is called a general Riemann sum. So in general, a Riemann sum will look something like this. You will have the sum from the first rectangle to the 50th rectangle of the width of each rectangle, delta xk, times the height of each rectangle, f of xk. And this can be applied for any partition. Doesn't have to be a regular partition. A general Riemann sum will deal with any sort of partition, because as the number of rectangles gets larger and larger, as you try to cram more and more rectangles into that same space, it's really not going to matter after a while if all of the rectangles are the same width or if they are different widths. So the partition's not going to matter as the number of rectangles approaches infinity. So the definite integral looks something like this, and here is its definition. If you have a function that is integrable means able to take an integral, and the limit as delta x approaches 0 of the Riemann sum exists. For all partitions, doesn't have to be a regular partition on a closed interval a to b. Then the definite integral looks something like this. You see the similar integral notation with this elongated s here. So we say that this is the integral from a to b of f of x dx is equal to the limit as delta x approaches 0 of the sum from k equals 1 to n of f of xk times delta x. So basically, the definite integral is an infinite Riemann sum. The definite integral is the sum of an infinite number of rectangles. And remember, as the number of rectangles approaches infinity, the width of each rectangle, delta x, approaches 0. So if you were to take the limit as delta x approaches 0 of this Riemann sum, you would get the definite integral. So as far as where this notation comes from, you have to remember that calculus was not all, invented all at once, that calculus was not developed all at the same time by the same person. Calculus was really a variety of advances from a variety of different people over a large span of time. So Leibniz is actually the one that came up with this elongated S notation. Now, in Leibniz's time, the concept of limits was in its infancy. It wasn't called a limit at the time, it was actually called an infinitesimal. So because limits were a concept and weren't really developed yet, the limit notation, this right here, also didn't really exist. So Leibniz came up with his own way of expressing the sum of an infinite number of rectangles. He came up with his own way of expressing the sum of an infinitely number of infinitely small rectangles, which is this elongated S, that integral symbol. So basically, Leibniz, who didn't have this notation, because the sigma notation didn't exist either, and neither did the limit notation, Leibniz expressed this concept as the integral symbol from a to b. And as delta x gets smaller and smaller, delta x approaches dx, and as the number of rectangles gets larger and larger, f of xk just becomes f of x. Because this notation here, this integral notation, is so beautifully compact, we do use it instead of, this mess here on the left with the limit and the sigma notation, just because it is so simple and so compact. Now just remember that as delta x gets smaller and smaller, delta x becomes dx, exactly like it did in derivatives. So here are the various parts of the definite integral notation. We've got the integral symbol, that elongated s. X equals a is what is called the lower limit of integration. It is the left endpoint of your interval a to b. Now x equals b, this number here on the top, is what is called the upper limit of integration, and that is the right endpoint of your interval. F of x, which is the function that you are taking the integral of, is called the integrand. And x here, this part that follows the dx, this is called the variable of integration. And remember, in this class, this is one variable calculus. Whatever variable your function is in terms of needs to be the same as your variable of integration. So this variable here needs to be exactly the same as this variable here. And the definite integral will give the exact area between a function's graph f of x and the x-axis on a closed interval a to b. Integrable means able to take an integral. So if f is continuous on a closed interval or bounded on a closed interval with a finite number or with a finite number of discontinuities, then f is integrable. Now, there are a couple of different ways to evaluate definite integrals. We're going to look at an algebraic way in a little bit once we get a little bit more background. And you can also evaluate definite integrals using geometry. If the function itself and the region between the function and the x-axis on a specific interval forms a geometric shape, you can use basic formulas from geometry to evaluate that definite integral. So for this first one, we have the linear function 2x plus 3 over the interval 4 to 2. So if you were to graph this, the line 2x plus 3 would look something like this. And then if you were to section off the area between x equals 2 and x equals 4, you would form a region like this. This right here, this shaded region, is called a trapezoid, and the area of a trapezoid formula goes something like this. You have 1/2 times h, which is the distance between the parallel sides, times the length of parallel side number 1, plus the length of parallel side number 2. So that's basically what we're going to be using to evaluate this definite integral. So the distance between the bases h, the distance between 2 and 4 is 2. This height right here between the x-axis and this point is going to be given as f of 2. And this height right here between the x-axis and this point is going to be given as f of 4. So the area of this region is going to be 1/2 times the distance between the bases 2 times the length of parallel side number 1, f of 2, plus length of parallel side number 2, which is f of 4. So if you were to evaluate f of 2 is 7. So 1/2 times 2, times 7, plus f of 4 equals 11. And then if you were to evaluate all of this, 1/2 times 2 times parentheses 11 plus 7, you would get 18. So the area of that trapezoid is equal to 18. So that means the area of the region bounded between our function f of x, the x-axis, and x equals 2 and x equals 4 is going to be 18. Now I will say that we are going to be getting an algebraic way of evaluating integrals like this that's actually really easy to do, that does not involve using the area of a trapezoid formula. But evaluating integrals using geometry can come in handy when algebraically it would be really difficult to find to evaluate the definite integral algebraically. For this next one, I will say that evaluating it algebraically is a nightmare. So if you can recognize that this is a semicircle, it'll actually make your life a lot easier. If you take a look at the square root of 1 minus x minus 3 squared, that is actually a semicircle. It is a semicircle with radius 3, 0, with a radius of 1. So a semicircle with a radius of 3, 0 and a radius of 1 will look something like this, where this is 2, 3, and 4. And then the radius here is equal to 1, so this height up here is 1. Now, if you're taking a look at the region between x equals 3 and x equals 4, if I were to shade the region between x equals 3 and x equals 4, it would be this. This is a quarter circle. So because this is a quarter circle and you know how to find the area of a circle, we're just going to find the area of a circle and divide it by 4. So the area of a circle is pi r squared. Since what I have shaded here between x equals 3 and x equals 4 is a quarter circle, I'm just going to divide it by 4 or multiply it by a quarter. So the radius of that circle, 1/4, the radius of that circle was 1. So the area of that quarter circle is actually going to be pi over 4. Now, since this shaded region was the region that was indicated in the definite integral, that means this definite integral is equal to pi over 4. So what that means is that the area of the region between this function, the x-axis, from 3 to 4, the exact area of that region is equal to pi over 4. Now, just like Riemann sums, which always gave you the net area, definite integrals will also give you the net area. So if you have any part of your function that is below the x-axis, any regions that are below the x-axis are going to have negative areas. So if you are taking the definite integral of a region where part of it is below the x-axis and part of it is above, just the definite integral will always give you the net area. It will consider any areas below the x-axis as negatives. So what I have here is a generic f of x, and I have various regions, the areas of various regions given. So the area between a and b above the x-axis is 12. The area between b and c below the x-axis is given as 10. And the area between c and d above the x-axis is given as 8. And what we're going to do is we are going to use this little bit of information to find each of these integrals. So first off, starting with the integral from a to b of f of x dx. Remember, a definite integral is the exact area between a function's curve and the x-axis from x equals a to x equals b. So what this first definite integral is asking is the exact area of below this function from x equals a to x equals b. So the area is given as 12. And since that area is above the x-axis, it is going to be a positive 12. So we say that this definite integral is equal to 12. So then for the next one, we are looking for the integral from b to c of f of x dx. So what this is saying is find the exact area between f of x and the x-axis from x equals b to x equals c. So from x equals b to x equals c, this area between the graph and the x-axis is given as 10, but since it is below the x-axis, it is actually going to be a negative 10. So this integral is equal to negative 10. So then for the next one, if you have the integral from a to c of f of x dx, what it's saying is find the net area between the graph of f of x and the x-axis from x equals a to x equals c. So from a to c, part of it is above the x-axis and part of it is below the x-axis. And it switches here at b. So because it is a clean cut here at b and there's no gaps or overlaps between these two pieces, we can simply take the integral from a to b and add to it the integral from b to c, and then that will give us the integral from a to c. So first, starting with this area between a and b, it is given as 12 above the x-axis, so that'll count as a positive 12. Then we are going to add to it the area between b and c, and since that is below the x-axis, we're going to be adding to it a negative 10. So then 12 plus negative 10 gives us a net area of 2. Definite integrals just by themselves will always ever give you net areas. So what that means is there is slightly more area above the x-axis than below the x-axis. So 12 plus negative 10 will give you 2. So then for this last one, we're looking for the integral from b to d of f of x dx. So this is asking for the exact area between f of x and the x-axis from x equals b to x equals d. So from b to d, it breaks apart here at c, so it switches from below the x-axis to above the x-axis here at c. And since it is a clean cut at c with no gaps or overlaps between these two regions, we can simply take the region between b and c and add to it the region between c and d. So first, starting with the area between b and c, that is going to be given as negative 10. Plus, we're going to add to it the area between c and d, which is given as 8. And since it is above the x-axis, that is going to count as a positive 8. So the net area is going to be negative 2. When you get a negative net area, that means that there is more region below the x-axis than above the x-axis, and a definite integral will always ever give you a net area. Now, a couple of properties of definite integrals. If you need to switch the bounds for whatever reason, the smaller number really should be on the bottom. If the smaller number is not on the bottom for whatever reason and you do need to switch the bounds of integration, you can, as long as you make it negative. So if you want to switch the bounds of integration, you just put a negative sign in front and you switch the bounds of integration, and that negative sign in front will count as a constant multiple. Now, if the bounds of integration are ever the same, so if you have the integral from a to a of f of x dx, I don't care what your function is, if your bounds of integration are the same, there is no region, so its area is 0. So if the bounds of your integral are the same, the integral is always equal to 0. Now, a couple other properties of definite integrals. This one is pretty much the same as indefinite integrals. If you have a sum or difference inside of a definite integral, you can always split it up into the sum or difference of two separate integrals. Just notice that each of the bounds do remain the same. Also, just like constant multiples could come out of indefinite integrals, constant multiples can come out of definite integrals. So if you have a constant multiple c times your f of x, you can write it outside of the definite integral. Now, this next property we pretty much already used. So if you have a region and it's broken apart at c, then if you're trying to find the integral from a to b and it's broken apart at c, all you have to do is find the integral from a to c, so this integral here, and then add to it the integral from c to b. And this will work as long as there are no gaps between the pieces and no overlap between the pieces. This is especially handy when your function transitions from one side of the x-axis to another. You can simply add the two regions together as long as they meet here at C, with no gaps and no overlaps. Now, another very similar property is called the subtractive property of definite integrals. So let's say that you were trying to find the area of the region between A and B. And you know the area between the larger area between A and C and this smaller area between B and C. So if you were to take the larger area between A and C, subtract out the area between B and C, you will be left with the area between A and B. There we go, got the subtitles working again. Now remember, a definite integral will always ever give you net area. If part of a region is below the x-axis, it will count as negative. The biggest application of this is in velocity and displacement, because remember, velocity can be negative. That means displacement can be negative. So any negative directions traveled will count as negative distances. If you want to, let's say, find the total distance traveled and you don't care about distance, you will need to take all of those negative displacements and turn them into positive displacements. So if you take the integral of an absolute value of f of x, what that will do is it will take any regions that are below the x-axis and it will mirror them above the x-axis. So if you take the integral of an absolute value, it will make any negative areas positive areas, and then an integral of an absolute value will be, let's say, total distance traveled, which doesn't care about direction. So this slide here, which remember is on Canvas, was just a kind of summary of all of the different rules of definite integrals that we have so far. Remember, if your bounds of integration are the same, doesn't matter what the integral is equal to 0. If you need to switch the bounds of integration, you can, as long as you put a negative sign in front. If you have a sum or difference inside of a definite integral, you can split it up into the sum or difference of two separate integrals, just keeping the bounds of integration the same. If you have a constant multiple c inside of a definite integral, you can take it out of the definite integral and write it in front as a constant multiple. And then if you need to find the area between a and b and it is broken apart at c, you can simply find that region by taking the integral from a to c and adding to it the integral from c to b. Notice how these two bounds are the same. And if you take the integral of an absolute value, it will take any negative areas and mirror them over the x-axis to become positive areas. So for this next one, we're going to just use this limited information that we have about f of x. I'm not telling you what f of x is. You do not need to know what f of x is. We're just going to use this little bit of information and our integral rules to find each of these integrals in parts a through d. So I am giving you that the integral from 0 to 5 of f of x dx is equal to 3. So the area of the region between 0 and 5 of f of x and the x-axis is 3. And the integral from 0 to 7 of f of x dx is equal to negative 10. So what I'm going to do is I'm going to use that information to evaluate each of these. So starting with part A, we have the integral from 0 to 7 of 2 times f of x dx. This 2 is a constant multiple. Constant multiples can always be written outside of an integral. So I'm actually going to rewrite this as 2 times the integral from 0 to 7 of f of x dx. Well, the integral from 0 to 7 is actually equal to negative 10, so this will give us 2 times negative 10, which gives us a final integral of negative 20. Now this next one is actually going to involve the subtractive property of integrals. So we are looking for the integral from 5 to 7 of f of x dx, which we are not directly given. But we are given the integral from 0 to 5, and we are given the integral from 0 to 7. So we know the integral from 0 to 7. We also know the integral from 0 to 5. So if we were to take the integral from 0 to 7, and we were to subtract out the integral from 0 to 5, we will be left with the integral from 5 to 7. So that's exactly what I'm going to do. I'm going to take the larger area between 0 and 7 of f of x dx. I am going to subtract out the area between 0 and 5, so the integral from 0 to 5 of f of x dx. And then that will leave me with the area between 5 and 7. So the integral from 0 to 7 is negative 10, minus the integral from 0 to 5 is 3. Negative 10 minus 3 will give us a net area of negative 13. So then for the next one, remember on definite integrals, the smaller number should really be on the bottom, so we need to switch the bounds of integration. If we're going to switch the bounds of integration, we can, as long as we put a negative sign in front. So I'm going to put a negative sign in front, and I'm going to switch the bounds of integration from 0 to 5 of f of x dx. So the integral from 0 to 5 is 3, but since we needed to switch the bounds of integration, it is actually a negative 3. So then for this last one, we need to do a couple of things. First of all, that constant multiple of 6 can come out of the integral entirely. Also, if we have the integral from 7 to 0, the smaller number should really be on the bottom. So I want to switch the bounds of my integration, and I can as long as I make it negative. So I'm going to take the 6 out and make it negative and switch the bounds of integration from 0 to 7 of f of x dx. So we get negative 6 times the integral from 0 to 7 they gave us is negative 10. So negative 6 times negative 10 gives us a final integral of 60. All right, so that is it for definite integrals. We're not doing too much with them yet. We are going to do more with them once we cover the next section, which is the fundamental theorem of calculus, which actually links together indefinite integrals and definite integrals and really outlines how those two are related to each other. I'm sorry that the subtitles were so glitchy. Remember, you can always turn subtitles on YouTube by selecting the closed captioning feature and then just selecting subtitles. So thank you all very much for watching, and I will see you in the next video for the fundamental theorem of calculus. Bye-bye.